Hey everybody, this is Mr. Bortnick for AP Calculus AB. This is Unit 1, Limits and Continuity, and today we're on topic 1.12, confirming continuity over an interval. Enjoy today's notes. All right, for today's lesson on 1.12, confirming continuity over an interval, we're going to start with some notes before we get into the packet. I want to remind us from Algebra 2 and Honors Algebra 2 of different ways that we can represent intervals, and specifically how we do that in AP Calculus. And so one common way that we talk about intervals of x values is by using inequalities. And so, that's, talking about things like x is greater than 5, x is greater than or equal to 10. So this would be x is greater than 5, or x is greater than or equal to 10. And so, inequalities are great for talking about things that are less than or greater than, or even things like compound inequalities, where we might say that x is between two numbers. For example, we might have like -2 is less than or equal to x, which is less than 5. So this is saying that x is between -2 and 5, but notice it is also equal to -5, or -2 rather. So inequalities are super useful. Just a reminder, if you ever do use inequalities that, especially compound inequalities, they're normally written with the smaller number on the left, so smaller number, and then the larger number on the right. And that's if you're doing compound inequalities. So this is an example of a compound inequality. Otherwise, we just have regular x is greater than 5, x is less than whatever. Normally in those cases, if there's just one thing, normally you'll see the x always coming first, always on the left side of those things. Okay, so inequalities is a common way that we've been using for years to talk about ranges of numbers or domains of x values. The other way that we probably were introduced to last year in Algebra 2 and Honors Algebra 2 is what's called interval notation. And this is the most common way that we are going to talk about intervals of numbers in AP Calculus. Sometimes you'll see inequalities, but most of the time we're going to be using interval notation to talk about sets of numbers or lots of different values. And this is pretty much the standard for AP Calculus. They will most of the time use interval notation. Sometimes they'll use inequalities, but those are really the only ones that we do. What does interval notation do? Well, specifically, there's two parts to it. So we use parentheses, like this or this, to represent endpoints of intervals that are not included. And similarly, we use what I refer to as brackets or square brackets, like this or like this, to represent endpoints that are included. And so let's take a look at this. I'm going to sort of compare two different ways of looking at this. So one would be the inequality notation, and we'll compare that to interval notation, which is going to mean the exact same thing, just in a different way. So here are some examples. Let's so if we were to say x is greater than 5. So x is greater than 5. The way that we would write that in interval notation, we say, okay, we start with our lower number first. So 5 is the lowest number, comma, it's going to go all the way up forever and ever and ever, because x is greater than 5, all the way up to infinity. And so I notice here, looking at this inequality, that it doesn't equal 5. And so because of that, it's going to get a parentheses. And it can never actually equal infinity as well, so we always put parentheses on infinities or negative infinities. So I'll mention that on the side here. Always parentheses on infinities because we cannot equal infinity. We can approach it, but we can't get there. And then the other tip that I also gave as well is we always put the smaller number first. All right, so that's one example of this. Let's talk about a different one. What if we were to say that x is less than or equal to -2? Well, if x is less than or equal to -2, that means, it can be all the negative numbers below that. And the smallest number that we would have here is going to be -infinity. It would go all the way down to -infinity. And in this case, the largest number on that interval is going to be -2. We know that it can't equal -infinity, so it gets a parentheses on it. But we do notice that it does equal -2 from that inequality, and so we put a square bracket on that -2. That is how we'd represent that as an interval. Well, what if we wanted to now say that x is between and equal to -3, but it's less than 100? Well, in this case, since x is between those two numbers, those numbers would be the endpoints for our interval notation. So -3, 100, and again, from least to greatest. And since it's equal to -3, it would get that square bracket. Since it's not equal to 100, it would get the parentheses for that. What if we were going to say, let's do one more of these. If we were going to say that that x is between -7 and 40. Both of those are equal to each other, so -7 and 40 are two numbers that are the endpoints of our interval. They're both equal, so they both get square brackets. And then actually, for real, our last one now. What if they're not equal to either of them? Well, let's say x is between -1000 and 2. Well, those are the endpoints of our interval. So -1000 and 2. We put a comma between them to separate them. And since they're not equal, these are both going to get parentheses. Now, I want to point out here to be really careful when you're reading problems in AP Calculus to determine whether or not they're talking about a coordinate or they're talking about an interval. Because if we take a look at this last interval that we've got right here, notice that it's got parentheses on both sides. It would be really easy to confuse this with a coordinate, right? The point, -1000, 2. But normally in problems, they will say the word interval or the word or the point if they're talking about a coordinate. So while these two would look similar, it's really important for you to take a look at the context of a problem to talk about whether or not they're talking about a coordinate or an interval in this case, since they both use a comma and they both use parentheses on the outsides in cases where they're not equal to each other. It's very easy to confuse, so be careful. All right, let's move on to our notes. Finding the domain. So if we're going to confirm continuity over an interval, we're going to need to think about what the domain is going to be for a particular function. And in this case, there are three scenarios to watch for when looking for a restriction on the domain. So these are cases where we might have some limitations on the input of a function. Remember from last year that the domain is the set of inputs for a function. Right? And range would be the set of outputs for a function, but the domain is the set of inputs for a function. So if we're thinking about restrictions on the domain, we need to think about some cases where a function, we wouldn't be able to plug in particular values. One of those that we would need to be careful of is denominators. And specifically, we know that they really cannot equal 0. And so an example here, we know in this case that x plus 1 in this denominator could not be equal to 0. So that means that the domain of this function is that x could not be equal to -1. So that would be an example where it could be any value of x, but it cannot be -1. And that's what we call a restriction on the domain. A second one that we need to worry about is specifically for even roots of radicals. Even radicals, or square roots. So an example of this would be the square root of 7x plus 3. We might remember that generally the part that's under the square root would need to be positive, right? We can't take the square root of a negative number, at least not without complex numbers. So if we're talking about, just general numbers, real numbers, we know that whatever's under that square root symbol needs to be positive. And so, or it could equal 0 as well. So 7x plus 3 in this case would need to be greater than or equal to 0. And so if we subtract that, that means that 7x is greater than or equal to negative 3, and that x would have to be greater than or equal to negative 3 over 7. This would be the restricted domain for that particular function. X could be any value that's greater than or equal to negative 3 over 7, but it cannot be anything that's less than that because it would make the part under the square root negative, and that doesn't work for radicals. Why did we say even here? Well, sometimes we might remember that we've got radicals that are like cube roots, or things like fourth roots or fifth roots. It could be really any root. This rule only works only is something to worry about in even radicals. It doesn't matter in a cube root. You can have a negative under a cube root of a function, and it would still be defined. We know that for regular square roots, like what we've got right here, that even though we don't say it, technically this is a square root, that we could put a little 2 there on that to emphasize that it is a square root. But we don't, because it's assumed that that's what we're talking about when we see that symbol. Cool, let's talk about the third one. Third one, we've got a natural logarithm. So this is a natural logarithm, ln. And so the third case that we've got is really any type of logarithm. Any type of logarithm. And to think about the restriction for this, I want to just point out what the graph of a logarithm looks like. Let me zoom pretty far in just so we can see this. So we've got, actually let's undo this. So we've got our lines. We've got this equation. The general log of x equation, if you look at it, if you graph that function, it's going to look like this. This is the general shape of this. It goes through the point 1, 0. And what's a feature of a logarithmic graph that we should know? Hopefully from our logs chapter from last year, is that one of the key defining features of a log function is that it's got an asymptote at the line x equals 0. This graph never gets to 0. And so because of that, the domain of a logarithmic function is, whatever's inside of the log has to be greater than 0. It has to be greater than 0 based on that graph and based on that function. It doesn't matter whether it's a regular log or a log of a particular base, or in this case, a natural logarithm, the inside would have to be greater than 0. And so because of this, I know that 2x plus 1 has to be bigger than 0. It can't even equal 0 because of that asymptote. And so if we subtract, we get 2x is greater than negative 1, which means that x is greater than negative 1/2 would be the domain for that last value. Great. Let's move on to finding the domain of each function here. I noticed that we've got a fraction for this first one, so we know that that denominator cannot be equal to 0. So because of that, I know I'm going to write that x cannot be equal to 0 if we're finding the domain. And then the two ways that I would really write this, one way we could write this is going and thinking about that interval notation that we were talking about. In interval notation, we're saying, okay, well, it can be any value other than 0. It could be less than 0, or it could be greater than 0. And if it's less than 0, it could go all the way down to negative infinity. And it can go all the way up to 0, and it can't equal 0, so I put parentheses there. Or it can go from 0 all the way up to positive infinity. And the way that we write both of these things together is we use this thing, this u, between the two of those, which is what's referred to as a union. So the u between these two sets of interval notation is essentially math for and. It's both of those. They're together. So it's negative infinity to 0 and 0 to infinity. And we use that union symbol in order to show that both of those would count. Alternatively, we might use set notation, which we didn't talk about earlier, but you might have seen this with in last year. We might say it's all the set of real numbers. So this is the set of real numbers, except x is not equal to 0. So this would be a different way that we could write this. This is not nearly as common. It doesn't show up really on the AP exam, but I know that some of our students prefer writing it this way, and so you are welcome to do that on quizzes, tests, or the AP exam. But if you're learning one method, the way that will most pop up is going to be that interval notation. I would do it this way if I were learning it from the first time. Cool. Let's think about number two. Number two, we've got this numerator, we've got this denominator. First off, we know that the denominator cannot equal 0, so I know that x cannot equal to 0 because of that denominator. But we also notice up in that numerator that we've got a square root. So we need to be careful because we also know that the square root cannot have a negative under it. So because of that, I also know that x plus 5 has to be greater than 0 or equal to 0 from our radical rule, our second radical rule that we've got here. So I also know that x has to be greater than or equal to -5 if we subtract that on both sides. So sort of two key pieces, both of these, x is not equal to 0, but x is greater than or equal to -5. If I was going to do this with interval notation, our lowest number would be -5, and it is equal to that. It can go all the way up to 0, but it cannot equal 0. And we put the union between those. It can go from 0 all the way up to infinity. So this would be our interval notation. That's the way that I would write our answer for number 3, or number 2 rather. Number 3, let's take a look at this. What's our domain? Well, I've got sort of two issues. I know that the whole denominator cannot equal 0. So 2 minus the square root of x cannot equal 0. And so if I were to add that to their side, 2, where is that the case? That's 2 is equal to the square root of x. And if we square both sides, that would be when x is equal to 4. So I know that x cannot equal 4, otherwise that's going to be a problem. But also, we have this square root. And we know that whatever x is cannot also be negative under that square root. So because of that, I also know, because of the square root, that x has to be greater than or equal to 0 because of that. So I have these two values. And again, I would write this in interval notation, and I am going to do that. So our lowest number that could be is 0, and it goes all the way up to 4, but it doesn't include 4. So we're going from 0 to 4. 0 gets that square bracket because it's equal to 0 in that inequality, and it cannot equal 4, so it does not get the square bracket, it gets a parentheses. We put a union between these, and then it can go for anything bigger than 4 as well. So from 4 all the way up to infinity. That is going to be our interval notation for problem number 3. What about number 4? Well, in this case, first off, we know that we've got a fraction inside that denominator. I know that x minus 4 cannot equal 0, otherwise that's going to make the denominator 0. So I know that x cannot be equal to 4. That's our first rule that we've got for this. But we also know that we've got a natural log. We've got a logarithm. And as we had written up here before, logarithms, the inside of the logarithms cannot be negative. They have to be positive. So I know that x divided by x minus 4 has to be positive. It has to be bigger than 0. Now, there are two ways that this could be the case. Thinking about how a fraction works, right? If we think back sort of even like to grade school, that if it's going to be positive, I could have a positive being divided by a positive, and that's going to give me an answer that's positive. Or it could be a negative divided by a negative that is going to cancel out and become a positive. So it could be either of these two cases. And so we would need to think about, what values of x would make that true. Well, our first case where they're both positive, anything where x is greater than 4 would make that denominator and that numerator both positive. That would be positive over positive. Alternatively, we could make the numerator negative, and if the numerator is negative, any x values that's negative in the numerator would also be negative for the denominator. So in that case, anything that's less than 0 would give us a negative over a negative for that, which would cancel and give us a positive. So what is our answer using the intervals, right? We're taking these three things into account that we've got here. So x could be less than 0. So it can go all the way down to negative infinity, all the way up to 0. It's not equal to. And x has to be greater than 4, but it can't equal 4. So our other choice is going from 4 all the way up to infinity. And we put the union to say that it's both of those, that it's negative infinity to 0 and 4 to infinity. Now again, remembering this interval notation, what are we talking about here? We're talking about inputs. We're talking about x values. We're saying that it's continuous, or it has a domain for any of those x values between negative infinity and 0, and from 4 to infinity for that interval notation. All right, number 5, where is this function continuous? Well, we've got a couple different pieces here that we need to look at. Specifically, I would check first, I'm worried about, is it continuous at 0? Because it's two different pieces of our piecewise function there. Also, I'm worried about, is it at 3? Because we've got two pieces of our piecewise function coming here. But we also need to look at the equations themselves, right? Are there any things that would make limits on our domain? And specifically, I notice it's got a denominator in 2 of these that we need to worry about. So I know right off the bat that x cannot be equal to 7 for this second equation. Right, x cannot be equal to 7 because of this second equation. And given that it's actually not part of this interval, that's not something we need to worry about too much. So I'm going to actually, cross this off and say we're not going to worry about that, because that's only bad for x is greater than x is equal to 7, and that's not on the interval that we're looking at for that part of the equation. However, if we take a look at the denominator of our third equation that we've got right here, we would have 4x minus 20 is equal to 0. We don't want it to be equal to 0, which means that 4x cannot be equal to 20, and x cannot be equal to 5. That is on this interval that we've got here. So we do need to be careful, and that is going to be one that we're going to need to worry about here. So that's one piece that we are going to need. In addition, we want to check to make sure that this function is continuous when x is equal to 0 and x is equal to 3. Like what we did in the last section, if it's going to be continuous, we would need the two parts, specifically this part of the function, to be equal to this part of the function when x is 0. So let's check that out. X squared minus 2x minus 1 over 7 would have to equal 3 over x minus 7 when x is equal to 0. So when x is equal to 0. So I would have 0 minus 1 over 7 is equal to 3 over negative 7. Is negative 1 over 7 equal to negative 3 over 7? No. So I know for sure that it is actually not continuous at 0. And so that is a point of discontinuity for this function. And so that is a second place where it is discontinuous. I'll just highlight there. We can check with 3's, so I'll do that real quick. Similarly, we need to check when x is equal to 3 because there's two different parts of the piecewise function there. So I need to know, is this equation equal to this equation when x is equal to 3? And I'll do that here in blue. Let's see, so 3 over x minus 7 should be equal to 7x minus 15 over 4x minus 20. If we plug in 3, so this is when x is equal to 3, we would have 3 over 3 minus 7, which is negative 4. And then 7 times 3 is 21 minus 15 should be 6. 4 times 3 is 12. 12 minus 20 is negative 8. Oh, hey, 3 over negative 4 is equal to 6 over negative 8. That's good. So x equals 3 is fine. So the only 2 points that this cannot be, we're going to just sort of say it is everywhere continuous. Whoops. So everywhere continuous except x equals 0 or x equals 5. And we could write that with interval notations as well, but that's going to be our answer for number 5. We've got some practice problems for you to try here. Try those out, check your solutions, and do your mastery check. Come on by to office hours or bring questions to class if you've got any, and have a great rest of your day.